So good afternoon everyone, and thank you for coming to this Chair's Distinguished Seminar Series. I'm really delighted to welcome today's speaker, Professor Wygnanski from the University of Arizona. No stranger to this area. In the morning, I really enjoyed half an hour. I think I'd like to talk to him for another 2 hours. A very interesting career. It started in McGill, then it went through British Columbia to Seattle, then back to Tel Aviv, then to Arizona, but all related to some exciting events and very, very exciting talk and interesting talk I had. So by way of education, Professor Wygnanski got his doctorate degree, undergraduate and master's degrees from McGill University, PhD in 1964. And then in his career, he has had many distinguished awards, such as the next year's AI Biden Lecture, the 2015 NASA Associate Administrator of Aeronautics Award, etc. There's a long list. I had the pleasure of listening to him when he won the Meyer Henning International Prize given by the Technion. He gave a very exciting lecture. And I think you will hear a similar lecture. So, without going through that list, I also want to say he's a member of the National Academy of Engineering, and he's been in the Aero department at Arizona since the early 80s. So, without further ado, I welcome Professor Wygnanski to give us this lecture.
The title is a bit long, but I'll try to explain what is a fluidic fence. A fluidic fence is basically a use of one or a couple of small number, let's say, of sparsely spaced jets that emerge from point sources. And they act like a curtain, if you wish, like a jet curtain. And by that, in that manner, they control a little bit of the span-wise flow on a finite wing and so on. I would like definitely to acknowledge a couple of students of mine, Marvin Jench and Bernard Ronch. Both are from originally from Germany, and a couple of postdocs, Philip Teves, who was actually just a student, and Lutz Taubert. Let me start being controversial. I feel here is a question. Is aerodynamics a sunset science? And if you look, and there are, from commercial airplane point of view, as an outsider, you could say, yeah. Why? Because and the real question is the following. If I have a mission which is described, I need to take payload X over a range Y at a speed Z. If I put it in a computer, can I get an answer, and maybe you can tell me, can I get an answer what the wing shape should be? And if that's the case, then I would say aerodynamics is, and you can't do anything, then aerodynamics is a sunset science. Well, backing that statement, which I personally feel is incorrect, but will be the following. When the last real paradigm shift occurred in terms of airplane design, specifically let's go to commercial airplane design, and the big paradigm shift was introduced by Busseman, and it's the swept-back wing because it delays the drag rise due to Mach number. And if you go back and you look at this airplane, this is a 707. It flew already in 1954, I believe. It rolled as a 707 or Dash 80. And before that, it was already KC-135. And if you are just a casual observer and you say, well, how different is an airplane today from this? And you say, no, nothing. Can go further. Here are new airplane wings There is the Mitsubishi regional jet on top. There is the A320neo. There is the Russian MC-21. There's the Boeing 737 MAX, I believe, and 787. And you say, look at those wings. They all seem to be identical. And perhaps they use the same CFD program too, because the pylons are almost at the same location. Everything seems to be scaling very the same. So here it is. Take then another example. Take the 777-200ER and take the Airbus and compare the wings, and here it is. So what you come up is that we sort of are saturating ourselves in perhaps we came to the optimal design, and that's where we'll be stuck in, and that's it. Look even further. Because there is the wish for a commonality of parts, look at the A320 family of airplanes. All that was added, essentially, as far as the airframe is concerned, was a piece of tube in the middle. And only in the case of the 318, which is really short, that a little bit of the vertical tail was added there on top, and a horizontal tail was increased. Okay, but the rest, you see, and that's so. If you really go further and you say, and we recently had this experiments with vertical tail, you take all the vertical tails of all the Boeings that I know, and all the Airbuses that I know, and put them together, and there's what you get. There are only very small differences between competitors already. So that would say, yeah, aerodynamics became, as far as these type of airplanes, became as mature science, let's be polite. Are there any misconceptions that guide this design? Well, I can say two of them that I see. There probably are more. One of them is a statement that turbulent flows forget their origin. In other words, if I do something somewhere on a wing, because the flow is turbulent, that the effect of whatever I will do will disappear relatively shortly thereafter. And I think this is partly the basis to many of the U-runs, the CFD models that are used, that are primarily looking at the local condition. So I believe that this is a misconception. And the second misconception is this idea that if we have a wing, which is a very large aspect ratio, essentially in the limit, infinite aspect ratio, in laminar flow we make a statement that there is a principle called the independence principle, and it doesn't hold in turbulent flow. And there's enough articles that it doesn't hold for 50 years, I think, or more. And I believe this was incorrect. So let me elaborate a little bit about these two issues. First of all, this turbulence forget its origin. So here, let's say we take a strip of metal, put it in the wind tunnel, a solid strip, and put downstream of it a smoke wire. This is what you see here. Is there a laser pointer on that? Well, anyway, so there is a solid strip. Then we take a perforated strip of metal, again stretch it along the same tunnel, and we adjust the size of that second strip of metal in such a way that the drag of these two strips, the one at the bottom and the one at the top, is exactly identical to within 3 significant figures. So far away, the wake depends only on the drag, right? So if the wake velocity profile is some kind of a bell shape, then there is a product of the velocity scale and the length scale that represent the drag, and therefore there is a statement that all these wakes should be universal. Well, are they? Look in here, that's the smoke wire pictures. The two wakes are very different. The product is exactly the same, but one is much wider than the other. And so what happens here at the origin is remembered, even though that flow is very highly turbulent. And in fact, you can see also for the smoke wire, the smoke here goes upstream, the smoke over there doesn't. So there is that stability already affects the flow downstream. As a good example, there was recently in, I think in the Spiegel, a map showing the wake of Madeira. And it's very similar to the typical Kármán vortex street, except that, you know, if the statement could have been made that whatever we observed before is a low Reynolds number, well, every eddy in that is of the order of 100 kilometers. So that's a pretty good Reynolds number, if that's it. And on the right of this, you can see all kinds of wakes produced by bodies of different shapes that have the same drag, and you can see how the width of the, quantitatively, how the wake changes from one wake to the other. So that is not a correct statement that all the turbulence flows forget where they originated. No. The large-scale eddies have a very, very long memory. And by the way, that belief is still quite universal. I was asked to review an article just 2 months ago that wants to prove that all wakes are the same, universal. Oops. How come I did something here? Oh, thank you. Why did... Okay, now to go to the other thing that I believe is a misconception. There were experiments when swept deck wings started being of interest in the 1950s. There were experiments carried out on flat plates that were changing the sweepback angles from 0 to 45 degrees. And all the data collapsed at the same all the data collapsed, if we normalized by some length scale here, collapsed on the properly. So the experiments were done correctly. What happened is that the interpretation of those experiments, I think, was incorrect. And it yielded to the statement that because, you see, the Reynolds stresses in these two equations include both this V prime component in both, that the equation for the spanwise flow and the equation for the chordwise flow component, if you go and decompose the free stream into two components, that both of these are coupled, and they are coupled because the V prime fluctuation appears in both of them. Well, that's true that they are coupled, and yet if one goes through the proper equations, one can prove that the independence principle, which is saying that, you see, the chordwise equation here doesn't have any W or any dependence on Z. If the aspect ratio is infinite, then in fact, if there will be no coupling between this V prime, then you can analyze the two boundary layers separately. In fact, that this spanwise component is dependent, the chordwise component is independent of the spanwise component. Now, what happens is that you cannot just take a simple transformation, cosine transformation, go along, but you need to consider that if you have two boundary layers, then you have to consider the losses of each of those two boundary layers. And if you sum them vectorially properly, you get out the proper result that the length scale that comes out here, if you choose momentum thickness, that it is representative of the drag coefficient if it is non-dimensionalized by the free stream. And when you do it, that's what happens. And in fact, we did this not only then we took another experiment which was done at NACA still, and we predicted what will be the angles at which the span-wise flow, the flow near the surface will occur, and those are the dots, the full symbols here. And indeed, you can see that agreed with the experiment, although there is a pressure gradient and so on. What does it tell us? It tells us that if we can look at the high aspect ratio wing, and we have two components to be concerned with, namely a component which is normal to the leading edge and component which is along the span. It will tell us, first of all, tells us where will we see a flow being dominated by the span-wise component. And here it is. It's actually dominated in the aft part of the wing, because a simple explanation is that the kata condition requires that the chord-wise component will become 0. So then the span-wise component dominates it, and you can see here the example given. What other problem it shows is that you will get accumulation of vertical fluid next to a tip of a wing if that wing is swept back, and that causes a lot of problems. And I'll address that in a few minutes. What is actually the problem of swept back wings? One of the biggest problems is low speed, because as you increase the sweep back, you notice that there is a pitch up problem, that the pitching moment, specifically let's say high sweep back of 45 or 60 degrees, pitching moment changes its sign abruptly. You can see here that change, and that's really uncontrollable. So because of that, there are various solutions found. One of the simplest solutions is, okay, so we need the sweep back for supersonic flight. We need good stability for landing approach, so we we change the angle upon landing. And this is on B1, this was on F-14, this was on MiG-23. On other airplanes, you take a very low aspect ratio wing with relatively low sweep back, then you don't have the problem. In recent years, or it's not so recent anymore, the F-18F and G had a problem of dropping the wing, so it was solved by NASA partly, or that's how they claim, by putting leading edge droops, which were also allowing air to go through them. In other words, they were not solid. If you take an empirical figure here showing what planform of wing is stable and what is unstable, you come up with a thing that here's an aspect ratio versus sweep back, and if that equation, aspect ratio times tangent of the sweep back, is larger than 2.6, expect instability. If it is less, maybe you will be stable. And however, what do we really want? We want to have an airplane that will have high aspect ratio. We would like to be somewhere here at the top right corner, and yet mostly we are using a design which is somewhere in here. So that's not, we would like to improve on this, and the question is, of course, how do you do this? Well, one of the problems of swept back wing is that the tip of the wing is highly loaded, so there is an attempt to reduce it. One attempt was simply to increase the chord at the tip, which is kind of odd, but it was done. That airplane flew. The Russians, in all their MiG series, had large fences, and if you look at the commercial airplanes, well, there is a Boeing patent that has this big fence here, and essentially what it does, according to the Tim Wang, I think is his name, patent, is that it produces a very large vortex over the upper surface of the wing, and therefore perhaps it eliminates the spanwise flow there. Embraer has vortilons just inboard of the aileron, and to make sure they also added a whole bunch of vortex generators over the upstream of the ailerons. So what that figure suggests, that essentially the most important parameters here are the aspect ratio in the sweep back and the shape of the wing platform. But we know that in airfoil design, you have the leading edge radius of curvature, you have the camber, and so on. So there should be other effects. But what it turns out to be that if you change all these, change the leading edge droop, you change the leading edge sharpness, the effect on the pitching moment is essentially the same, because you create a vortex at the leading edge that spills over, turns in the direction of the stream at higher incidence. So what happens is the same effect is seen, except that there's a difference at what angle of incidence it occurs. So here is the comparison between these three, and you can see the creation of that vortex is an increase in DCL, alpha. This is the figure here, and it also generates with it a pitch up problem. Now, when we went, thanks. That should be better. When we started on the vertical tail project, the idea was to put a whole array of actuators right in here and see whether we could improve the efficiency of a rudder. So this was a test carried out at Caltech, and we had 32 actuators along the span. We then disabled actuators, and we came down to something like 6 actuators. And what we saw when we looked at the force generated by the rudder versus the input momentum coefficient, that for very low momentum coefficients, if we had sparsely spaced actuators, we had a big effect. And the big effect was because we see that here the flow was attached, namely these tufts were very steady, and yet they were all pointing along the span, which means that the flow was dominated by the spanwise velocity component. So that is what led to this concept that perhaps if we have small number of actuators, we can do much better. And if we have only a couple of actuators, of course we don't cover the entire area here. So here is the experiment that showed the effect. And here you see 6 actuators, or we had 32 actuators. So the number of stars here suggests how many actuators were used. And the pressure contours are showing the difference between using active flow control, using these small jets, versus the baseline conditions. So if we had a large number of actuators, we had hardly any effect for very low input of momentum. But if you reduce the number, you can see there is a large effect here. On the other hand, if we had a high input, then a large number of actuators was appropriate. In other words, we asked ourselves, what are we doing here? Well, in this instance, if the rudder is highly deflected, we mainly control the chordwise component. We control flow separation in the classical two-dimensional sense. But if we have sparsely spaced actuators, we don't cover the area, we mainly stop the spanwise component. And that's where the concept of the fluidic fence came about. And this is when we this was the test that one gentleman here was present in. That was at the 40 by 80 wind tunnel. It became quite clear that the direction of the flow was changing as the actuators that were located along the hinge were active. And the most interesting one was when we put one actuator. We got a 10% or 9% effect on this very large vertical stabilizer. And the area of the nozzle of that jet was 1/8 of a square inch. The area of this whole tail is 370 square feet, so it's almost 500,000 to 1 in terms of area ratio. And yet, the effect is sizable. You put 3 actuators, you get to this point, you put 5, you get up there. And finally, because the success criterion required 20% improvement, 18 actuators or 37 actuators, I believe, did the job. But I think in the flight test, at the end of the day, 31 actuators were used. But what's significant is this one actuator, clearly all it did is had a jet going in this streamwise location, streamwise direction. And then you started looking at what happened. You look at old airplanes. This is the MiG-19. That's not boundary layer thickness. This is just stopping the spanwise flow. I mean, this is 18-inch high, okay? You look at the Cougar, you see a droop at the tip and a fence. So that is why you can have here a fence on demand, if you wish, when you want to go at low speed. And there is the picture from the flight test and picture of the tufts which were at the flight test, and the most recently, actually, Faye Collier, who was in charge of the environmentally responsible aircraft project in out of NASA. I got this award from Aviation Week. Well, we came back from that experience and asked myself, first of all, am I sure that it's tied to the sweep back? So we had a setup where we have a sweep back of 45 degrees, essentially a NACA 12 type wing, or non-swept. And if we used 2 actuators versus 29, if the wing was swept back, we got this result. If the wing was not swept, we got nothing. However, there was a crossover at the high momentum input of roughly 0.7% momentum coefficient. So clearly 2 actuators did a very interesting job. And so we started looking at the wing, and you say, okay, let's look at any lambda wing, sort of typical of a UCAV type, and let's look at 2 potentially big effects. What happens to this part, which is basically just tapered, versus what happens to this part, which is basically just swept back. And a typical lambda wing, we say, the first order of approximation, that's the combination of these 2. And we looked at various papers that were published and looked at the fact that here towards the trailing edge, the flow is all going into the spanwise direction, and we said, okay, so we need to control it from this region. So if you look at the tufts on this just swept deck portion, you can see the tufts are very nice and steady, but they go all along the span. If we lower the flap here, they become slightly unsteady and become even more directed towards the span. So that is flow visualization observation. And then if you look at the leading edge of such a thing, we see here is the pitching moment versus alpha, and you see that initially the flow is attached near the leading edge. Then a vortex is being formed somewhere along the span over closer towards to the tip, and there is an effect on kind of stabilizing effect, if you wish, because there's more lift created, and then more negative pitching moment, and then you get the rise, and you ask yourself, how come is this? Because if this low pressure goes and increases, it increases in both directions. So if it goes here and this is your axis of rotation, then yes, you stabilize the flow initially, and then if you cross with that leading edge vortex inboard, then you start getting the destabilization. So there is sort of trying to couple that flow visualization with sweep back. Then if we go only to the tapered wing, this is, by the way, Fluent CFD that suggests that if we have a flap here and just deflect it to 30 degrees, we get a flow which is attached, which goes inboard. If we deflect it more, the flow is still seem to be attached over part of this, and then again inboard, but weaker inboard than here, and then the separation occurs actually all over, just close to the root, and that is understandable. But what we had observed is that yes, indeed, if we just deflect this 30 degrees, you have this inboard flow at the root. But if you deflect it more, you create like a, let me call it for lack of better definition, a hinge vortex, because it is, most of the lift is generated here near this juncture and on that flap, which is deflected. And so you can look at this portion, if you wish, almost as a forward swept wing. And so you expect the flow to come this way. And yes, you create that hinge vortex, of course, that originates here, where that boundary layer is thickest, and propagates inboard. So you have a flow over a thing like that is outboard near the hinge and inboard near the trailing edge. And so how do we control a thing like that? Well, if we put in some actuators at the hinge and we look at various angles, you see that what basically those actuators do is they are aligning, this is the magenta type tufts here, they are aligning the flow in the free stream direction. So at small angles, they affect mostly that flow. At higher angles, they affect the flow near the hinge. And this is pressure-sensitive paint there. And you can see how the low pressure is generated by the very large flap deflection. However, that low pressure, by the way, being on the flap, which is deflected at 75 degrees, contributes mostly to the drag, not to the lift. What happens on wings is that if you have a flap on this low aspect ratio wing, you have a flap that you deflect beyond 30 degrees, the flap doesn't give you any added lift anymore. It just stalls here and does nothing. And you can see, however, that here is DCLD alpha, which every time it breaks, you can see that there is a increase in DCLD alpha is associated with creation of a vortex. In this case, it's a hinge vortex, and as a consequence, there is a departure here in the pitching moment. So, if we look at now at, say, various flap deflections, and you will look at lift for, say, 3 families of incidents, 0, 8 degrees, and 16 degrees, you can see that at already relatively low flap deflection, we get no effect, we get essentially stall. You put in actuation at the hinge, you can increase the lift by 15–20%. However, if you worry about the pitch-up problem, you see there is your baseline with no active flow control. Already you start having a pitch-up problem at lift coefficient of 0.6, and with relatively low input of momentum, you can go all the way to something like 1.1. This is almost a factor of 2 increase of lift without creating a pitch-up problem, and that's very substantial, because then it means that you can approach, your landing approach can slow down by a square root of that, which will be something of the order of 30%. So then we went to a second platform. That is, second stands from stability and control model. It was designed by DLR in Germany as an exercise for AVT, which is the NATO's sort of study group. And so that wing, if you wish, cannot really fly. Why? Because the way it was designed, it's to make it unstable. So if you do nothing, and by the way, it has a very sharp leading edge right in here, and then changing into blunt, and then slowly being sharp again. And what happens to the flow there is that you have like a vortex being slowly created at the root, but then most of this vertical fluid comes to the tail here, to the outboard part near the trailing edge. You increase alpha, you start seeing that now the leading edge vortex is being created at the tip. It enlarges. Here is your neutral point, and soon enough it penetrates through that, and there you completely lose control. So there is your pitch problems versus alpha, namely you get increase in pitching moment, then sudden drop, and then increase again. And the question is, can this be controlled in any manner? And the answer is yes. Just here, small number of actuators can bring this pitching moment from this black line to here, which means that essentially from an unstable situation you can create neutrally stable situation. You can see that if you put fences, 2 fences over here, you get the green line, so you get an improvement, but still insufficient. So this fluidic fence idea is a very good one. And then we started looking at pressure sensitive paint and distribution. So here is how we calibrated it. You see we had in situ calibration of pressure, and you can see what the contours did. So I would expect that qualitatively it's a wonderful tool, It shows you how the leading edge vortex is here generated, how it spills over towards the trailing edge, creating the large instability. Quantitatively, I would say this is correct within 100 pascals, and ISSI claims that it should be correct to within 10 pascals, but still it's a very good tool, much better than putting, say, 200 pressure taps in that wing. But here is what happens, and what you really want is to have, if this is your neutral axis, what you really want is to have as low a pressure here and as high a pressure here in order to avoid this pitch-up problem. And what happens actually is, as you increase the angle, you see that you create this vortex, and the way this vortex turns around towards the trailing edge, the arm becomes larger and larger because of the low pressure, and that's why you get this terrible pitch up and pitch control problem. Well, what active flow control does here? So you look at the tufts. We have here the actuators along that. There's no flap deflected in this case. And you see that it realigns the flow from being totally spanwise almost to totally chordwise. And if you look then at the pressure, this is the baseline pressure with the high pressure region in here. And you can see what the active flow control does. Actually, by entraining fluid here, it lowers the pressure, and so it lowers the pressure all along this area. So you subtract these contours from these contours, that's what you get. You get a lowering of pressure over most of the surface of the wing, outboard of that neutral axis, and that enables you to control the pitch. So that happens on the Sakon, and if you look at that situation, you say, okay, how many actuators do I need? Well, we had in there 13 actuators used, or we had only 4 actuators. And you can see that the 4 actuators up to a certain C mu, momentum input, did as well as the 13. So you can say, okay, without any flap deflection, I am somewhere here, and without any flap deflection, there is my lift versus pitching moment. So this is unstable even at 0 lift. Okay? And we move from here to here by using active flow control. But you can say, well, maybe I can fly with the flap down. So if you move that flap by 20 degrees, you move from this black curve to this black curve, which makes it stable over up to CL of 0.4. But if beyond that, you are again unstable. So the thing is, if you do together under controlled situation, both flap deflection and active flow control, you can increase the lift coefficient when you fly from 0.25 roughly, maybe to 0.8 almost. So if you cruise at 0.25, you have lift to and use active flow control, you have lift to drag ratio of the L over D of the order of 13. And then if you want to land and use all that devices, you can still keep the stability, and you of course then reduce the L over D. So that's a very interesting outcome that came from all that. Then since the leading edge vortex is something of that people do see, and the question is, can we maybe control that? We see it more as a symptom than the actual sickness, if you wish, Because what it does, if you have an actuator right in here of the same type, you in fact, here is how your jet goes. It increases the pressure over most of the region that you are interested in, decreasing the pressure. So you get, in fact, a deleterious effect. If you look at higher incidence here, you can see that this is much stronger. So treating the leading edge, although theoretically should be good, it is much, much harder than treating the surface, which is, let's say, aft of the half chord here. Because that, it's easy to do. However, what we did observe is that if you have actuators here at the leading edge, we do control the leading edge vortex. But elimination of the leading edge vortex is not really what we may want, because it gives us lift, and if the flow is controlled downstream, we don't have the added pitch up problem. So basically, by putting actuation at the leading edge, yes, we can delay the leading edge vortex creation. You can see it here, the DCL, the alpha is constant up to a higher angle. This is the baseline. This is using actuation. We can also weaken the leading edge vortex, but I'm not sure that this is what we really want to do on some kind of a combat aircraft configuration. The only one more thing I want to say here is that if you just use active flow control, there is an interest. The question is, can we control an airplane? Can we change the flight path without having any control surfaces deflected? Because apparently there's an observability problem. And so apparently, well, you can use active flow control, create rolling moment and yawing moment, maybe small, but definitely that will lead you to change your flight path without deflecting the typical control surfaces. So here are my first conclusions, is that pitch up at low speed, that it's a major impediment to design of swept-back wing, can be alleviated. I think that the independence principle that suggests that span-wise flow on swept-back wings could be treated differently, should be treated differently from the chord-wise flow component. I think that's a good indicator here that was provided by that. And it provides guidance also to where to put the actuators. We also see that we can have a trimmed flight and we can change the direction because we change the yawing moment and the rolling moment. And what I would like to see is that active flow control should be considered as preliminary design tool that may change structures, they may change the shape of the wings to come. So my conclusion here is that active flow control may open a new era, if you wish, in the way that aerodynamics is used, and could be an enabler of new designs. Thank you.
We can ask floor is open for questions. Yes.
I wanted to make sure I understood. I think on the trailing edge jets, those are actually at the full trailing edge of the configuration, right? So the flow they're putting out isn't going over the wing at all, it's trailing behind it. Is that correct?
The flow near the trailing edge of a highly swept back wing, let's say something of the order, sweep of the order of 40 degrees, near the trailing edge is mostly in the spanwise direction outboard, from the root out.
But the jets you had on there, are they right at the trailing? They were labeled trailing edge jets. Were they
The jet was directed in the chordwise direction, and it's deflected by the free stream, eventually curving in the direction of the free stream. So the flow over the surface is then redirected, depends on the strength of the jet, if you wish, redirected more inboard, and then usually it ends up to be just in the direction of the free stream.
I think he's just asking where the actuators are on the cord. I think he's just asking where the actuators are on the cord, and they're upstream from the trailing edge.
The actuators, the most convenient location of the actuators is if you consider a wing that has also control surfaces and flap, is at the hinge. And actually just upstream of the hinge, because there you have much more volume than on the, and it's easier also to introduce the actuators to a stationary place and so on. Okay, and the major question is actually in the applicability is, where do you get your air supply and how much air you need? You see, if you use very small number of actuators, the amount of air is small. And there are now developments actually in Europe where you can have compressors that are 12.5 centimeters in diameter, electrically driven, and supplying up to 1 kilogram per second at pressure ratio of 2.2. Now that's huge relative to what we have seen, because essentially one such thing can cover a big area now. So that's where possibly there may be an application. Yeah?
Did you look at the effectiveness of the system relative to free stream velocity?
Can you repeat, please?
Did you look at the effectiveness of the system relative to free stream velocity? I would assume it's a passive.
Yes, we did. And let me say the following. The momentum coefficient is a good representation. However, if you have large area, then your velocity ratio relative to the free stream is low, and you need at least a factor of 3 velocity ratio in order to be effective. On the other hand, if you go into nozzles that are choked, you get into another problem. Because first of all, you lose a lot, and we use these sweeping jets, you lose a lot of pressure within the actuator. Secondly, you get shocks on the outside, and the jet entrains much less. It's compressible, supersonic jets entrain less than subsonic ones. So there is an optimization issue. But there is an optimization issue also in the exact location, or the distribution, if you wish, of actuators along the span and so on. But, if we improve our understanding of what we do, you can see it as your, say, incidence increases, as your velocity drops, you can switch easily from one jet location to another jet location, from a single jet to maybe 3 if needed, and so on. So that whole thing is really, open for future design. But we still, frankly, we don't fully understand what these sweeping jets do, because it's a jet that oscillates back and forth without any moving parts. How can we affect that? And how it interacts with the boundary layer, which is on the verge of separation. So there are few people do work on this aspect, but it's still not very clear what is happening.
Other questions for Jim?
From the standpoint of operability, you're flying at low speed on approach, for example, and say your system fails.
And the what?
The system fails. So the active flow control has gone out either on the entire wing surface or on one side. What's your sense of the implications for the flight? Are we talking inconvenience or capacity?
It depends, first of all, what surface you are looking at. If you have just a flying wing, you better make sure that you have a couple of systems so that you have, if one fails, the other one gets in. Huh? No. Like having 3 computers on an airplane, right? So if one fails, they vote, right? Or this is what I understand happens, right? You don't use only one computer to control the airplane.
Basically backup systems.
Yeah, I would say if it is on horizontal, if it is on a vertical tail and the engines work, then there's no problem. You don't need the size of the vertical tail that's on today's airplane, except for the thing, the unfortunate incident that you lose an engine. That's what determines really the size. But if it is on a horizontal stabilizer, that may be a bigger problem. If it's on a wing, and particularly for naval applications where you would like to reduce the speed on approach to an aircraft carrier as much as possible, it has huge implications. I have only learned recently that some airplanes return, and if they are a little bit too heavy because they return with their ordnance, whatever it is, sometimes electronic pods and so on, they just drop them in the sea, so there goes millions of dollars can go in a situation like that, just because otherwise they cannot land. And so, on certain surfaces, horizontal stabilizer or wings, if you can just reduce the speed a little bit, the big effect.
Another question there?
A lot of commercial airplanes have leading edge slats, and some of them are gaps, some of them are not, depending on the landing configuration, takeoff configuration. Have you looked at the combination of using these fluidic devices with slats in positions?
Usually, if you have slotted flaps or slats which are separated, active flow control is less effective because the air that you entrain from the lower surface interacts, So I would say it would be better to use droop leading edges without any gap between them, or simple flaps. So that is for simple flaps, it's definitely an advantage because you don't need then these actuators which hang underneath and so on. So the interaction between slotted surfaces is usually, I would say, deleterious.
Okay, thank you very much, Dr. Wygnanski.